All right, this is day 6. So we started a little bit of this on Wednesday at the end of our marathon session. All right, those will be few and far between, but we just needed to do a little bit of catch up here. Just to quickly review what we were doing is talking about conditional probability. And we said we're talking about givens. When we're talking about conditional probability, what the given does is basically it shrinks our sample space. Okay? Rather than dealing with the entire situation that we were dealing with, we're narrowing our focus. So out of just this subset, what's the probability of something happening? Okay, so we have this formula here, and I wanted to just run through this example real quick again to illustrate our formula. Because when we have a table like this, we actually can think it through a little bit logically as well. But let's start first of all with the formula itself. We're going to do the probability that the sum of the two dice is prime, given that the first die you get is even. Okay? So this is just an example here. And using our formula, the probability of both over the probability of the given, okay? What we would be doing here is we would be finding the probability that the sum is prime and the first die is even. Okay. Over the probability that the first die is even. Okay. So we're looking for an intersection first. So if we call this one right here the first die, all right, these are the results of the first die. Okay. I'll get you set up. Okay. Then we have how much of a chance that that first die is even?
50%.
Yeah, 50% chance, okay? So our denominator here is going to be 1 out of 2, all right? Or 3 out of 6. It's a 1 in 2 chance that we get an even number, 2, 4, or 6, okay? But then, as we look down those columns, okay, we will find the intersection, okay? So just to kind of illustrate here, if I look at all the prime numbers, I have 2, I have all my 3s, I have all of my 5s, I have all of my 7s, these are all my primes, and then I also have all my 11s. So those are all the prime sums. But then I also have when the first die is even. So I have all of these. Okay? So the intersection, the probability of the intersection is going to be these ones where it overlaps. Okay? Alright, so those 7, I think I got them all. Yep. Those 7 are the number of ways that I could have a prime sum and an even die in the first die. Okay? So, as a result, I have a 7 out of how many chance? Out of 36 chance of being in the intersection. Okay? So now we simplify here, and if you flip that 1/2 and multiply, you'll get 7 over 36 times 2, so that's 7 over 18. We have a 7 in 18 chance of having a prime sum given that the first die is even?
I think I'm just
Yes.
confusing myself right now. What do you mean the first die is even?
You roll 2 dice. And the first one that you roll, that's either even or odd, right? And then after you roll the second die, you're going to add the 2 dice together.
Oh, so just the sum of, okay.
Yeah, so the sum of them is prime. Okay? Now, let me illustrate for you another way of thinking through this that I think actually makes these ones where you have a table, or as we'll see in our next example, when you have a Venn diagram, it makes them much easier. Okay? And that is, if we consider the given, and think about that in terms of the given narrows our focus, it narrows our sample space. Okay? So if I look at my given and I narrow my sample space down, I'm narrowing it down to the occasions when the first die is even. All right? So I'm narrowing it to these cases right here. Okay? Now, how many different rolls are there? That I just narrowed it down to? Well,
18.
6, 12, 18. Yeah. Okay.
Rows.
No, how many rolls? Sorry, rolls. So here's 6 different rolls I could get. We're rolling a 2 first. Here's yeah, rolls, not rows. Sorry. Okay, so now out of those 18, what is my probability of getting a prime number? Well, then if I go back and just look at those 18, I've got a 3, a 5, a 7, a 5, another 7, a 7, and an 11. There are 7 of the 18.
So do we have to show that work beforehand, like 7 out of 36? 7?
Well, here's the deal. On this, no. If you have a table and you can figure it out logically like this, that's great. All right? The problem is you're not always going to have that. So knowing how to do it with the formula is important too. And we're going to look at 2 different examples here next to see a case where you can do it logically and a case where you'll have to use the formula. Okay?
Could you explain it again? How do you get the 7?
How I got the 7 was I only looked at the 18 that I had narrowed it down to. And the prime numbers, I know it's hard because I'm shading over shading, but we have 3, 5, 7, 5, 7, 7, and 11. So out of these 18 that I narrowed my sample space down to, there are 1, 2, 3, 4, 5, 6, 7 out of those 18. Okay? And it was the same thing I got here. It's just a different thought process. Okay? Let's look at another case here with a Venn diagram. And when you have a Venn diagram like this is another example where you can use more of a logical approach to it. Okay? So here we have a class of 25 students. 14 like pizza. So we'll call this set P for pizza. And 16 students like iced coffee. So we'll call this C for coffee. 1 student likes neither of them. And 6 students like both. All right? So before we go on to the rest of the problem, let's fill in our Venn diagram. Okay? What am I going to do with that 1 person who doesn't like either of them?
In the box.
Yeah, they're going to put them in the box. Okay? There's that 1 person. They're in the box, but they're outside of both circles because they're not part of either of those groups. Okay? All right? So there's that person. What can we do next?
the people in the middle who like both.
Good, we put the people in the middle who like both. This is P intersect C, right? That's the middle, okay? Now, here's the crucial part. If 14 people like pizza, what goes in here?
8.
8, okay? We already have 6 of those 14 people accounted for, so 8 only like pizza. And by the way, putting it in those terms is helpful for you. These 8 people only like pizza. These 6 people like both, which means how many people only like iced coffee?
10.
10. All right? 10. Okay? So notice you have a total of 16 people liking coffee. You have a total of 14 people liking pizza. And add them all up. 10, 6, 8, and 1 adds up to the 25 students that we had. Okay? So now, what's the probability that somebody likes pizza if we pick someone at random?
Wait, I'm sorry, how'd you get 8 and 10 again?
8 and 10?
Because 14 people like pizza, but 6 of those people also like coffee.
So only 8 of them only like pizza.
Yeah, this is only pizza, and this is only coffee. Okay?
0.31% chance.
Okay? So what's the probability they like pizza?
31%.
31%? Okay, so that's right, 14 out of 25. Something's not right with 31.
I don't think more people like coffee than pizza.
Why not?
14 out of 25?
Wait, are you saying it just likes pizza or?
Well, no, it doesn't say just likes pizza, it's how many people like pizza. Okay, or what's the probability that that person likes pizza? Okay, so there are 14 people who like pizza. If we pick someone out at random, we have a 14 out of 25 chance of getting one of those people. Okay? You can convert that to a percentage. That would be 56%. Okay? So now here's the conditional probability. Given that he or she likes iced coffee. Let's change colors here so we can differentiate. Okay? Given that they like iced coffee. So what we just did here is we narrowed our sample space down. Okay? The given just narrowed the sample space down to these 16 people. Right? So we know that our probability is going to be out of 16. Okay? Here we're finding the probability that somebody likes pizza given that they like iced coffee. Okay? Now, out of these 16 people, how many like pizza? 6. Alright? So it's 6 out of 16. Okay? Again, we're figuring this out logically using the Venn diagram. Okay?
How would you read what's in the parentheses? The probability of.
The probability that somebody likes pizza given that they like iced coffee. Okay? Now, those of you who like to use the formula, that's fine. If you were doing this, you would need to use the probability that someone likes pizza and coffee, the probability of both, divided by the probability of the given. Okay? In this case, the probability someone likes coffee. Alright? So just working our way through this. What's the probability that someone likes both?
6 out of 25.
Good, 6 out of 25. What's the probability of that somebody likes coffee, period? 16 out of 25. So now you notice here, if we reduce this fraction, we can reduce a 1/25 out of both of them, right? So that cancels out, and we're left with 6/16, which again is 3/8. Okay, or if you want, 37.5%.
Wait, for the top part, why is it 60-25? Isn't it saying probability people like?
They like both,
Yeah.
would be 6 out of all 25 people.
So you have to say however many it's out of.
Yes, because here we're using just the straight formula. Up here we just put a 6 because we were using the logic. We narrowed our sample space so it was only out of 16.
Okay.
So out of those 16, how many people like pizza?
So
Just the
We
6.
always have to put how many it's out of if we're using the formula.
If you're using the formula, that's right. Okay? All right, so when you're given a table, when you're given a Venn diagram, you can use logic. All right?
Is there like a formula to find the intersection? 'Cause I don't think we went over that.
The formula to find intersection, you might have to use the combinatorics. You can use, a case like this where they tell you. If we have independent events, that would be the probability of the one times the probability of the other. We're actually going to see that with the next one here that we have to use the formula for.
But mostly it's just like sample space and stuff, right?
Yeah, mostly like if you have a Venn diagram, you can think of it in terms of sample space. Okay. Now here's just another quick example using the Venn diagram. Okay. We have 40 students total, 34 like bananas. So we'll call it, there's 34 for bananas. Here's pineapples. So this means these are the people who like the bananas and the pineapples. Okay. Now this one, the Venn diagram can be a little bit of a challenge. So I want to give you a minute here to try this. Okay, so someone want to talk us through how they filled it in? Harrison?
So I took 34 plus, I put 2 in the blank space.
Okay.
And then I took 34 plus 22. And that equals 56. And then I subtracted 56 from 38. Or I subtracted 38 from 56 and got 18. So both, they liked 18. I put in both.
Okay.
And then I subtracted 34 by 18 for bananas, which is 16 for the bananas, and then subtracted 22 by 18, which is 4 for pineapple.
Okay, good. If you just put 34 here and you put 22 here, you now have 56 plus 2, that's 58 people. And you're only supposed to have 40 people, right? So if that happens, notice they didn't tell you how many people liked both. Okay? They didn't tell you how many people liked both. You needed to figure out, okay, how many people must have been counted twice? That's what Harrison was doing when he did the subtraction there. Okay? 56 minus the 38, he had already taken out the 2 who didn't like anything. Okay? So he knew that the 2 circles combined accounted for 38 people. So that means there were 18 people who were counted twice. Alright? That's how we get the intersection. Once you figure that out, 18 plus whatever this is has to add up to 34. So that's where we got the 16. And 18 plus whatever this is has to add up to the 22 who like pineapple. Okay? So
I'm sorry, like, this might feel like a really stupid, where'd you get the 38 again?
the 38 came from the fact that we have 2 here. Okay?
Yeah.
So there are 40 students total, minus the 2 is 38 in the 2 circles combined. Okay, there are 38 people going to be in that part of the Venn diagram. Okay. Yes?
You solve through what you do.
Yeah, now let's think about this. Okay, A, we kind of did the hard part for, now we just have to identify it. What's the probability that somebody randomly selected likes both fruits?
18.
18 out of?
40.
Yeah, 18 out of 40.
45%.
Okay? 18 out of 40, 9 out of 20, or 45%. Okay? What's the probability they like at least one of the fruits?
38 out of 40.
Yeah, 38 out of 40, okay? 38 out of the 40 students at least liked something. Okay? Or 19 out of 20, which is 95%. Okay? Now, here we get to the given, and here's where the logic comes in. Alright, let's do part C in red. What's the probability they like bananas given that they like pineapple? Alright? So given they like pineapple narrows our sample space to just this part. Right? So my probability is going to be out of how many?
22.
22. So out of those 22, how many like bananas?
18.
18. Okay? So that right there, that gives us 9 out of 11, which is 81.8%.
Do you have that already worked out, or you did?
Well, 11's, easy way to convert 11's to percentages or decimals is take the numerator times 9. So 9, and then it repeats. So 9 times 9 is 81. So 9 elevenths is 0.81818181, and so on. So it's a little trick for 11ths. So, yes, huh?
How did you get the 18 for intercept section?
The 18, we narrowed the sample space just to the circle, and then inside this circle, there are 18 of them.
Why?
Huh?
Why did you get, how did you get 18?
The 18, that's what we did up here. There were 56 people total if you counted the 34 who like bananas and the 22 who like pineapple. But everything in these 2 circles should have only added up to 38. Okay? So we figured out that 18 must have been counted twice in the 34 and the 22. Okay? Alright, then we've got part D. We'll do this one in brown. Okay? What's the probability that they dislike pineapple? Okay? So the probability that they're not in P, okay? They dislike pineapple given that they like bananas.
Would it be 100%?
Okay?
Wait, isn't it?
Well, let's see, okay? If we like bananas, that means we're limiting our sample space just to these people, right? So it's out of how much?
34.
It's out of 34.
But doesn't that like cancel it because they're saying they don't like
Pineapple?
pineapples?
Well, look in this circle. How many of these 34 people do not like pineapple?
16.
16.
But wouldn't it be 16 out of 16 because they're saying given that he or she or dislikes pineapple and given that he or she likes bananas.
Yes. I think you're thinking that the given is dislikes pineapple. That's how I think that's what you're kind of thinking about. The given is that they don't, or that they do like bananas.
Okay, so
And then out of those, how many don't like pineapple? So it's these 16 people right there. Okay? It's a good question. Those are the things we got to work through here. Make sure that we understand. All right? Because figuring out logically with the Venn diagram here is really, really useful. It's great to be able to do, but you got to make sure you can do it right. All right? So, any questions about that one? Okay. So, at this point, we're going to be dealing with one where we can't use this nice little table, we can't use logic, we're going to have to figure it out. Okay? And this is kind of a silly example, but the applications are obviously a lot broader than picking a can of soup out of a cupboard. Okay? So let's read through this and let's think about it here. And we're going to learn how to use a tree diagram in order to do conditional probability. Okay? So it's the top shelf in a cupboard contains 3 cans of pumpkin soup and 2 cans of chicken soup. Alright, so here's our cupboard. We have 3 cans of pumpkin, 2 cans of chicken. The bottom shelf contains 4 cans of pumpkin and 1 can of chicken. Alright? Now, Lucas is twice as likely to take a can from the bottom shelf as he is from the top shelf. Suppose he takes 1 can of soup without looking at the label. Determine the probability that it A is chicken or B was taken from the top shelf given that it is chicken. Okay? Now to answer both of these, we actually have a case where using a Venn diagram is going to be helpful because really there's 2 decisions that are being made here. Okay? So, what's the first decision as he reaches into the cupboard without looking? What's the first pair of alternatives?
If he's going to the top or the bottom.
Yeah, is he reaching to the top shelf or reaching to the bottom shelf? Okay? So, we have the choice of shelf, top or bottom. Now, it says he's twice as likely to take a can from the bottom shelf as he is from the top shelf. So what would the probabilities be here?
1/3 and 2/3.
Is that what you were going to say?
Yeah.
Okay. So, 1/3 chance of picking from the top, a 2/3 chance of picking from the bottom. Okay? He's twice as likely to pick from the bottom. Okay? Does everyone get that part so far? Okay? Now, here's where we got to look at what's on each shelf. Alright? Because on each shelf, there's another decision. Does he grab a can of pumpkin or a can of chicken? Does he grab a can of pumpkin or a can of chicken? Now, let's think through our probabilities. On the top shelf, what's the probability that he picks a can of pumpkin soup? 3/5. And how about the probability he picks a can of chicken?
2/5.
2/5. Okay? By the way, 3/5 and 2/5 add up to
1.
1. Alright? Every branch of your tree, every choice here, should add up to 1. Okay? Just like 1/3 and 2/3 added up to 1. How about the bottom shelf? What's the probability it picks pumpkin?
4/5.
Good, 4/5. And chicken?
1/5.
1/5. Again, it adds up to 1. Okay? Now, here's where we need to actually, we're going to figure out a few intersections. Okay? So, for each branch of the diagram, let me zoom in here. We're going to figure out a probability. Okay? So, here we have the probability of top and pumpkin. Then we have the probability of top and chicken. We have the probability of bottom and pumpkin. And we have the probability of bottom and chicken. Okay? Now, we may not end up using all 4 of these, but they're so easy to find. I would recommend just always getting all of them. Okay? So to get each of these, we're going to multiply the probabilities along the branches of our tree. So top and pumpkin is 1/3 and 3/5. So 1/3 times 3/5 is 3/15 or 1/5. Okay? Top and chicken would be 1/3 times 2/5. So that's 2/15. Okay? Notice those don't add up to 1. Okay? Now, what's the probability of the bottom and pumpkin?
8/15.
What'd you say?
8/15.
Good. 2/3 times 4/5. 8/15. Okay? And then finally the bottom and chicken?
2/15.
Okay, good. 2/3 times 1/5 is 2/15. Now notice these do add up to 1. Okay, those are all the possible outcomes in our scenario. Okay, oops. All right, 3/15, 2/15, 8/15, and again 2/15. Okay, 3 plus 2 is 5, plus 8 is 13, plus 2 is 15/15. Okay, so those should all add up to 1. Now, does everyone understand how we got this tree diagram?
Yes, very much.
Okay. Once you have this, the rest of this is pretty easy. Okay? So, let's zoom out a little bit and address the actual questions. What's the probability that it's chicken?
4/15.
What?
4/15.
Okay, good. 4/15. If we're finding the probability that the can is chicken, we have to look at the different ways we could get chicken. We could get chicken from the top shelf, or we could get chicken from the bottom shelf. So we're adding 2/15 plus 2/15, and we're getting 4/15. That's the probability that we get chicken. Okay? By the way, did you hear I said or? We could get chicken off the top shelf or chicken off the bottom shelf. We're adding those two probabilities together. Okay? Now, here we have part B. Okay, let's change our color again. Part B. What's the probability that it was taken off the top shelf given that it's, given that we look in our hand and we find we have a can of chicken soup?
250.
Okay?
No. 2/3.
Well, let's look at it. How would we adapt our formula to this situation?
One
No,
half.
2/5.
Hang on, forget about the numbers for right now. Let's think about just the
You
formula.
have to look at the
Something
chicken
over 4.
or
No, it's 2/5.
The probability of,
Chicken overall.
yeah, that you look at the chicken first.
well, that's the denominator, the probability of chicken. Remember, it's probability of something over probability of the given. What's the numerator?
Oh, the two together.
Yes, the intersection. So top and chicken over the probability of chicken.
So 1/3 times.
Well, top and chicken is 2/15, right? So that's 2/15 over, what's our probability of chicken?
4/15.
4/15. That's what we just found, right? So what's 2/15 over 4/15?
1/2.
1/2.
Like I said, Harrison, please.
Okay? So we have, if we look in our hand and we find a can of chicken soup, you had a 50-50 chance of whether that can came from the top shelf or the bottom shelf. Okay? Now, this can be adapted. Obviously, which shelf, you might just tell them, hey, pay attention to what you're doing. And then you'll know exactly which shelf you got this from, okay? But this can be used for a lot of different things, For example, one common application of this is like when we're doing drug tests. Is a drug actually effective in treating a certain symptom? Or a test for a specific disease, okay? When we know the person has the disease, we know it's giving us a positive result this percent of the time. We also know that sometimes it misses people who have the disease, all right? Also with a test, sometimes you may not have that disease, but you get what's called a false positive, okay? They can do this kind of an analysis to judge how good a test is by saying, okay, what's the probability if someone gets a positive result that person actually does not have the disease? In other words, what's the probability we're going to scare someone for no reason? Okay? Or what's the probability that if it comes back with a negative result saying that they're okay, what's the probability they actually do have the disease? Okay? So, by the way, that's why they do all kinds of different testing and whatnot before they can get approved for lots of stuff, is because they want to get those percentages down as far as possible, to get the bad information down as far as possible. Okay? So these are kind of a simple example, but the applications are many. All right? Yes, hon?
How did you get the 1/3 and 2/3 for the first range?
This?
Yes, the 3, how did you get it?
That came from, when it said here, he's twice as likely to take a can from the bottom as he is from the top. Okay? You have to think, you can kind of do it logically, or you could think of it in terms of, okay, if this is his probability of taking it from the top, and he's twice as likely to take it from the bottom, and I know those have to add up to 100%, X is going to be 1/3. So I know he's got a 1/3 chance of taking it from the top. Double that, I have a 2/3 chance of taking it from the bottom. So you can set it up in a little equation like this, or you can just think it through logically I know it's gotta be the full 100%. If this has to be double this, that means I have 3 parts to this, so they're thirds that I'm dealing with. Okay. Any other questions?
Can you go back to the last page? I've got one.